Hello again, and welcome to another video. This one is going to focus on exponents and ultimately building up to what we do when units have exponents on them. But as with the other videos, we're going to start with hopefully the familiar and then work toward what might be less familiar or unfamiliar. And again, these are going to be the expectations that you find in general chemistry, that you'll be able to do these kinds of calculations pretty quickly in the first semester. So if they are unfamiliar, I encourage you to work diligently and really track these things. It will help a lot when you start classes to not have to be learning this stuff as we also learn chemistry at the same time. So with exponents and units, I'm going to again start with something that I think we know, that if we say something like 4 times 4, yeah, we could type that into the calculator and get 16. Again, I'm not interested in the actual numbers as much as in the symbolic representation of numbers and being able to manipulate those. But we're going to take what we do with numbers and then by logic extend that to what we do with symbols and units. So 4 times 4 can also be rewritten as 4 squared. 6 times 6 times 6 could be written as 6 cubed. Right? So we're familiar with that with numbers. Now, if we were to extend that to variables, let's say, if we were to do y times y, we could express that as y squared. So we see a direct correspondence to whatever we're doing. Wherever we see the number 4 here, we can plug in the number y and it works just the same. We could similarly substitute x for 6, and we have, that's a little confusing, x times x times x, and that would then be x. So the 6 gets substituted out and the x gets substituted in, and we would have x cubed in that instance. And we could even plug in, things that aren't mathematical or something nonsensical, like if we were to take ice times ice, we would get, that's right, ice cubed. So we can do this with anything. We could say desk times desk would be desk squared. We could even do symbols. So if we use the at sign, at times at times at times at, we've got 4 of them. So this would be at to the 4th power. Right? So the logic here extends beyond just the numbers, and that will be useful when we start dealing with units. Now, again, you probably have seen why this works, I'm going to transition now rather to multiplication and division when we have numbers, variables with exponents. So if we had something like 5 squared times 5 to the 4th, we could rewrite this then based on what we did above. We know that 5 squared really is 5 times 5. So that would be representing the 5 squared. And then we'd multiply by 5 to the 4th, which is 5 times 5 times 5 times 5. And what we see here is that we really end up with 5 times 5 times 5 times 5 times 5 times 5. Or we could write this more simply as 5 to the 6th. And again, we could type that into the calculator. I'm not interested in knowing what the number is, but in manipulating the exponents, because that's what we often do in solving problems. Okay. We could even do something like 36 to the 4th times 36 to the 9th. And here we start seeing the benefits of using exponents, which is simply that it makes these things easier to type. There's no mystery to exponents. It's just easier to write 36 with the little 4 raised to it, rather than if we were to really try to express this, look at how succinct that is. If we really wanted to write this out mathematically, we would have to say this is 36 times 36 times 36 times 36. That's our 36 to the 4th. And then we'd have times, and then we'd have 36 times 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 36. 1, 2, 3, 4, 5, 6, 7, 8. I need one more. 36. So this just simply looks a lot prettier than this. And in fact, I would argue that this is even easier to understand than that. And what we would see then is if we were to write it out like this, that we could write this as 36, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of these. So this would be 36 to the 13th. So we could come back here and say 36 to the 4th times 36 to the 9th is 36 to the 13th. More generally then, if we were to say something like x to the 15th times x to the 6th. We're beginning to see a pattern develop though. When we said 5 squared times 5 to the 4th, that ended up being 5 to the 6th. And it's not coincidental that 2 plus 4 is 6. So when we have a number raised to an exponent times that same number raised to another exponent, if we just add the two exponents in the case of multiplication, we add the two exponents and that becomes the exponent in the answer. So here when we had 36 to the 4th times 36 to the 9th, we could count them all and come up with 36 to the 13th. Or we could simply say, well, this is 4 plus 9 because we had 4 of them here and 9 of them there, and they all got multiplied together. So we have 36 to the 13th. So following that logic then, what do you suspect x to the 15th times x to the 6th is? That's right. That's just x to the 21st. And again, when we multiply numbers, and this has to be the same number as that or the same symbol as that, we are adding the exponents. And we can extrapolate this to, again, nonsense kinds of things. If we had a pound sign or hashtag to the 7th times hashtag to the 9th, what does that equal? Hashtag to the 16th. Right? If we say pillow to the 4th power times pillow to the 5th power, this would be pillow to the 9th power. So again, while we are maybe familiar with doing this with numbers, the important thing here is the logic that it also extends to variables that we kind of are familiar with, and then it even extends to words and numbers and symbols, so we can really apply it in any instance. Okay. But notice here that the pillow and the pillow have to be common. Hashtag and hashtag, we'll talk about what happens if they're not the same, but in this case, they are the same. And if we start trying to talk a little bit about chemistry or math, we could even say something like if we have kilograms cubed times kilograms to the 5th as units on some numbers, perhaps, that would be pretty unusual, but if that were the case, then we'd have kilograms to the 8th would be the units on the answer. Another instance, centimeters times centimeters times centimeters. This is a setup for the next video that I'll talk about. If we have centimeters times centimeters times centimeters, that is exactly like x times x times x, or 4 times 4 times 4. We're pretty content to say that that's 4 cubed. Then we should be pretty content to say that that's x cubed. And then just by extension of logic, that would be centimeters cubed. So all we're doing is saying whatever is in there, if I substitute this, that symbol, just blindly substitute, I don't even have to know anything about math. You know, if somebody just says, hey, whatever you see here and what we do to the exponent, do the same thing with anything you see in place of the number 4, you can figure it out in terms of what has to happen. Now, in this case, or in the next case, you might be asking, well, what happens if we don't have kilograms and kilograms? What happens if we have different things? So we'll go back to what we know. Numerically, let's say we have something like 3 squared times 4 squared. I have seen in some cases people wanting to just, well, do by extension what I did before. 2 and 2 is 4, so I'm going to put a 4 up there. And there's a multiplication sign here, so I'm going to take 3 times 4 and say that that's 12, and then the answer is going to be 12 to the 4th. And I just want to say that this is incorrect. and we can prove to ourselves that this is incorrect. And this is one of the big things I want to emphasize in this video, is that when you're in doubt about symbols or how to handle units, plug in numbers instead and see if what you're doing with the units works with numbers. And if it doesn't work with numbers, then it's not going to work with units. So what do I mean by works? Well, at this point, I would encourage you to do the following. Pause the video, calculate 3 squared, calculate 4 squared, and then calculate what that multiplication equals. And then separately calculate what 12 to the 4th is equal to. And ask yourself, are those two things equal? And if they are, then this is legitimate. And if they aren't, then this is, I would say, bogus or not allowable, mathematically not correct. Okay. So go ahead and pause, do that calculation. Okay, well, 3 squared, might not even need to calculate that. That's 9. 4 squared is 16. And if we take 9 times 16, I'm going to double check myself here. I did this earlier, but just to make sure, 9 times 16 is in fact 144. And then we ask, is that actually equal to 12 raised to the 4th power? And 12 raised to the 4th power is 20,736. So we would be saying, if we assert that this is the correct thing to do mathematically, that 144 is equal to 2,000 or 20,736. Clearly not right. Okay, so this is not legitimate to do. And the point that I'm trying to make here is that this and this have to be the same number. If I have 3 squared times 3 squared, that is in fact equal to 3 to the 4th. And that goes back to 3 times 3 times 3 times 3 is what 3 squared would be, and that's 3 to the 4th. We would not say 3 times 3 times 4 times 4 is equal to 3 times 4 to the 4th. We wouldn't be inclined to do that. So it only works, adding the exponents only works when the numbers are the same, or the symbols in the case of like kilograms, or the symbols in the case of centimeters. So similarly, x to the 5th, y to the 6th, if you see that, now we know we should not write this as xy to the 11th, or x times y to the 11th. A completely incorrect thing to do. So sometimes knowing what the limitations are is just as important, so that we avoid making those kinds of mistakes on exams or when we're problem solving. So that's multiplication. I will turn our attention now to division. So let's say we have 4 to the 7th divided by 4 to the 4th. Again, you might know right away that this is numerically equal to 4 to the 3rd, and if you do, that's great. If you don't, that's fine too. We'll figure out why it is, in fact, equal to 4 to the 3rd. Well, if we look at what 4 to the 7th is, we'd have 4 times 4 times 4 times 4 times 4. 1, 2, 3, 4, 5, 6. Need one more. 4 to the 7th divided by 4 times 4 times 4 times 4. And we know that when we have division, we can do some cancellations. So one of the 4s cancels a 4 in the denominator, another 4 cancels another 4, another 4 cancels that 4, and that 4 cancels that 4. And what are we left with? We are left with 3 4s, which we could express as 4 cubed. It would be 4 times 4 times 4 over 1 would be in the denominator. And as we saw in the last videos, anything over 1 is just the number itself. If we have x to the 5th over x squared, you see that this is equal to x times x times x times x times x over x times x. We do the same thing. X cancels. 2 of them in the numerator cancel 2 in the denominator. The denominator is now 1. So we're left with x times x over 1, which is x cubed over 1, which is x cubed. And what we are beginning to see now is a general pattern for division. Notice that when we divide 7 minus 4, so if we take the exponent in the numerator minus the exponent in the denominator, we get the exponent to the answer. So here, this could be rewritten as 4 raised to 7 minus 4, or 4 cubed. Similarly, x to the 5 minus 2, or x cubed. So when we multiply, we add exponents. When we divide, we are subtracting the exponents. So now we can broaden this to symbols. So I'll just use the dollar sign. Dollar to the 9th divided by dollar to the 4th. That would equal what? 9 minus 4, dollar sign to the 5th. So that's kind of nonsensical. We often don't deal with something like that, but we might have problems where we have miles cubed over miles. The exponent, when it's not stated, is implied to be 1. So in this case, we'd have 3 minus 1 is 2. So the answer here is miles squared. And again, if it helps to see why, it's like warming up to sing, me, 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 me. Sorry, that just occurred to me. Miles would cancel miles and we'd be left with miles squared. So when we divide exponents, numbers with exponents, we have the number itself, or the symbol itself, raised to the difference in the exponents, always defined as numerator minus denominator. So just like multiplication and division, this does not work if we have different symbols or different numbers. So we can't say x to the 4th over y squared. We would not want to say that this is something like x over y squared 4 minus 2. That doesn't work. Okay. X to the 4th over x squared, however, could be expressed as x squared. So the things have to, the symbols that we're working with have to be the same. And all these cases turned out to be positive exponents. There's no reason that they need to be positive exponents. We could have something like hashtag to the 3rd divided by hashtag to the 8th. And in this case, we get hashtag 3 minus 8. 3 minus 8 is negative 5. So we get hashtag to the negative 5. One of the things that I often see with some students is that, you know, we're uncomfortable with the negative signs. Like we like positive things, we like whole numbers, we don't like ratios, we don't like fractions, they seem inconvenient, they can sometimes be confusing. So the tendency is to just say, well, let's just ignore it. If you have that feeling inside of you, fight it, because we know it's not right. That feeling is there to tell us that we're doing something incorrect. And as much as we might want it to be easy, or what we hope would be easy, like this would really just be hashtag to the 5th, my life would be better because I don't like hashtag to the negative 5th. When you get that queasy feeling, just understand that you're probably doing something incorrect, and just pause and say, okay, 3 minus 8 really is minus 5, and I can handle that. So that's the expectation in general chemistry, is that things that might have confused you or you might not have wanted to really recognize, that we begin to correct those things. And they're perfectly correctable, and you're all capable of correcting those things. So that's the purpose of these videos, is to help with that, if that's the point you're at, and to succeed more easily when classes start. So let's talk about negative exponents then, because we are sometimes uncomfortable dealing with them. And I'll show you some tricks. I don't like them either. So what I try to do for myself is turn them into positive exponents whenever I can, and I'll show you how to do that. And the first thing that I'll show you is 5 to the negative 3 is equal to 1 over 5 to the positive 3. Now, you can memorize this, and you may well have already memorized this. But the other thing you can do, again, whenever you are not confused, but if you vaguely remember that this might be true and you want to know if it's true, rather than guessing, take out a calculator, plug in 5 raised to the negative 3. Okay, so I have not yet done that, so I'm going to do that. 5 raised to the 3 minus is equal to 0.008. Okay. So I do that, and then I'm going to ask, what is 1 over 5 to the positive 3? Well, 1 is 1. 5 to the positive 3 is 125. So now I have 1 over 125. Now if I take 1 divided by 125, I get 0.008. So I do come up with 0.008 is equal to 0.008. So I have a legitimate mathematical statement. I believe this. Right? That's true. Sorry, the camera continues to focus and defocus. I'm trying to be patient with it. There we go. So if I believe this statement, which I do, this is like 7 is equal to 7, then I believe this statement too. And now, now we can say, well, if it works for numbers, it works for symbols. We've proven that to ourselves. So in fact, if we have x to the minus 3, that's going to be 1 over x to the positive 3. So this is one way to get rid of negative exponents, or negative, symbols that have negative exponents, numbers that have negative exponents, turn them into the reciprocal fraction there. So if we had something like 19 raised to the negative 16th, that's sometimes hard to think about. I don't know what a negative exponent really means. Well, what it really means is 1 over 19 to the 16th, or 1 divided by 19 times 19 times 19 16 times. So it's going to be a very, very small number when you ultimately do that. Just to reiterate the point, x to the negative 7th would be 1 over x to the positive 7th. Right? So we've taken that negative exponent. Now we did, in fact, have to turn it into a fraction, so we might not like the fraction. So it really is a matter of preference as to which we want to deal with. Sometimes it's more convenient to deal with the negative exponent. Sometimes it's more convenient to deal with it as a fraction. And practicing doing problems will help you decide what is best for you to make sure you get problems correct. That's really what you want to do, is you want to adopt the method of treating these problems in a way that leads you to success. There is no right or wrong. This is right and that's right. They're both right. So it really is a matter of convenience. So now if we take something like 5 to the 18th times 5 to the negative 4th, we apply the same logic as we did before. If we simply say this is multiplication, so we're going to add the two exponents together, we could say that that is 5 to the 14th. 18 plus negative 4 would be 14. Or we could also think of this now as 5 to the 18th divided by 5 to the positive 4. And if we do that, we again apply the rule for division. We'd have 18 minus 4, which would be 5 to the 14th again. Right? So we end up in the same place. So lots of different ways to write things that are equal. So let's say we have s, maybe seconds, s times seconds to the minus 3. Why don't you go ahead and calculate what that would be? Simplify it. Well, one way to write this would be seconds to the minus 2, because we would have 1 plus a negative 3, or simply 1 minus 3. That leads to a negative 2. Here's another instance where we end up with a negative exponent, and hey, that's what we ended up with. We know 1 minus 3 is in fact minus 2. So we just have to write the minus 2, as much as we might resist the negative. We could also view this as seconds times 1 over seconds times seconds times seconds, which is seconds over seconds times seconds times seconds, which would be 1 over seconds squared. And we see that if we have a positive exponent in the denominator, then if we try to write that on a single line, if we don't want to write it as a fraction, then we have to acknowledge that it would be seconds to the minus 2. So that leads to another general principle. If we have something like 1 over shu to the fourth, this is equal to shu to the negative fourth. Or if we have 1 over banana to the negative sixth, so now if we have a negative in the denominator, it comes up, it would be a negative negative, so this becomes banana to the sixth. And we can see that because what 1 over banana to the negative 6 would really be is 1 over banana times 1 over banana times 1 over banana times 1 over banana times 1 over banana, 1, 2, 3, 4, 5 times 1 over banana, which would be 1 over banana to the positive 6. So we'd have banana, 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 banana in the denominator. But as we saw in the previous videos, 1 over anything is equal to that anything. It comes up, so we'd get banana to the sixth. You see how all of these general principles tie together and allow us to work more flexibly with symbols if we can make the analogy to how we deal with them with numbers. So we'll do a few more complex examples now where we do have some mixed calculations before ending this video and moving on to units. So let's look at x squared times y cubed over x to the fourth times y to the minus seventh. If we wanted to simplify that. Here, what we have to do is deal with like terms first. So we have x's in one case and y's in the other case. We can't mix them. We saw that we have to be dealing with the same symbol or variable. So if we look just at the y's first, we'd have x squared over x fourth, which is equal to what? Right, 1 over x squared, or that's also equal to x to the minus 2. So this part of the problem becomes x to the minus 2. And then if we look at the y's, we have y cubed over y to the minus 7. And again, I'll pause and let you calculate what that would be. So here we'd have y to the 3 minus negative 7. Negative negative becomes positive, so we end up with y to the 3 plus 7, or y to the 10th. So this whole thing equates to y to the 10th. So up here, this equates to y to the 10th. So our answer now would be x to the minus 2, y to the positive 10th, or this could also be written as y to the 10th over x squared. If you really wanted to, although we probably wouldn't want to, you could have this written as y to the minus 10th over x squared, or x to the minus 2 over y to the minus 10. But, again, since we don't like negative exponents, we tend to avoid that and probably prefer seeing that or this. Yeah, so that's how we can deal with more mixed problems. Lastly, we'll give you one to work on here, and I'll stop talking for a second. Try this one, y to the minus 3 times y to the fourth, z to the 10th, over y to the minus 3 times z to the fifth. Okay, hopefully you've either paused your video. If you haven't paused it and you're not done yet, you might want to pause it. In this case, we see that there is no x in the denominator, so we're just going to let that float and say that's x to the minus 3. Then we deal with the y's. Y to the fourth divided by y to the third would be 4 minus minus 3, which is y to the 7th. So our next term would be y to the 7th. And then we'd have z to the 10th divided by z to the 5th, which as we saw before, subtract, we'd get z to the 5th power there, or we could rewrite this as y to the 7th, z to the 5th over x cubed if we wanted to represent them all as positive. And you might say, so that's really it for this lesson, but one other question I just want to address, and I should have addressed this right away, is why do we do this in the first place? Why do we have negative exponents when we could really just turn them into positive exponents? And I honestly don't know the answer to that, other than I think it's due to typing. Because look, if we use a negative exponent, this is all on one line. You could type this. In Word, this would show up in a line. This is much harder to type. We could, I guess, say this, z, y to the 7th, z to the 5th, slash x to the 3rd, but this is harder to interpret, at least for me anyway, than that is. I don't see this as a fraction as easily as I see that as a fraction. So in my classes and in my professional life, I write all my fractions like this. I don't write them like this because this doesn't help me solve problems. And I would encourage you to avoid this notation and write things as fractions. But we use a negative exponent simply because when we were typing textbooks, when we, prior to the days of word processors, to be able to type something, we needed to have it all on one line. It was very hard to type on a typewriter a fraction. So I think the negative exponent is just a symbol to make things easy. So, if that helps demystify it, it really is just a simplification. So in the next video, we'll talk about how we apply this to units. And I, again, hope you found this useful. And I look forward to seeing you in the next video. And I encourage you to watch it because that's really where this learning will pay off. Hopefully much of this was review. And if not, that's great. But this will be very useful then to you on the next set of videos and when you start the semester. Thanks, and as always, have a great day.